Okay, hi guys, Mr. Rocco again. This is the third and final video for this week, the week of January 4th. And let me get started. This is on the greenhouse effect, which you've heard of. Greenhouse effect usually has such a negative connotation to it, but we do need the greenhouse effect. Without the greenhouse effect, Earth would be Pluto. We would be a ball of ice. So let me get right into the greenhouse effect. Talking about surfaces, lighter surfaces versus darker surfaces. So when it comes to insolation, and again, insolation meaning sunlight, energy from the earth, from the sun reaching the earth, darker, rougher surfaces are better at absorption. So I usually use the example of blacktop, right? Blacktop is a dark surface. It's got a rough texture to it, which allows the sunlight to penetrate into the surface itself. And so darker surfaces are better at absorbing. However, and this is where the second part is just as important, a good absorber, meaning a dark, rough surface, is also a good radiator, meaning blacktop will soak up the sunlight during during a bright sunny day, but once that sun sets at night, the blacktop that absorbed that sunlight will also get rid of it quickly. A radiator means to give off, right? Like the radiator in your bedroom that gives off heat, it keeps your room warm. So a good absorber is also makes for a good radiator. So blacktop, dark surfaces are good at soaking up sunlight, but are also good at getting rid of it just as quickly. And you can find that out when you let's say summertime and it's a bright, sunny, hot day, and if you step outside on your driveway, if you have a blacktop driveway and you step out on that blacktop barefoot, right, you're going to burn your feet. You're like, oh, wow, it's hot. But then if you wait and come back outside at night, give it a couple hours after sunset, and then go out and step on that driveway again, barefoot, in the summer, you'll notice that blacktop has cooled quickly. And so that's why that second part's just as important. A good absorber is also a good radiator. Things that soak up energy quickly also will get rid of it quickly, radiate it quickly. White surfaces are not the same, right? Ice and snow are good at reflecting, allowing the sunlight to bounce off of them. So ice, snow, things like that are better at reflection, not absorption. And that makes a huge difference. So if we look at the greenhouse itself, right? A greenhouse, right, made of glass. That glass is transparent, like our atmosphere is transparent. And so you think of the atmosphere like a glass greenhouse. It allows that short wave, high energy from the sun, that insolation, again, that's what this represents, this wiggly line coming in. This is going to be your insolation. It's going to be your sunlight. It allows it to go into the greenhouse as it goes through the glass. But then what happens is that greenhouse inside is going to convert some of that energy into heat, into infrared again. Infrared is heat. That's going to now trap a lot of that energy inside the greenhouse so that the sunlight will go through the glass, but then the heat, as it tries to escape, and it says down here, sunlight absorbs into the ground, changes it into heat. There's that infrared, and that's represented in this red arrow. It's going to be refracted. It's going to be reflected back. The glass is going to trap a lot of that heat inside the greenhouse and not allow it to escape. And so our atmosphere does that. Our atmosphere is good at trapping heat, and that's what those greenhouse gases are used for. So let me play this video about the greenhouse effect here. This is off YouTube.
Hi, it's Mr. Anderson, and in this video I'm going to talk about the greenhouse effect. And when you talk to people about the greenhouse effect, they tend to be pessimistic, but we really need the greenhouse effect on our planet. And so let me throw the sun out here, and then let's throw out the Earth. And so we're going to make this a black body. What does that mean? We're going to make this an object that absorbs all the light that's coming from the sun. So this is just theoretical. And so the scale is all wrong. The Earth is too big. It's way too close to the sun. But if we were to just imagine the Earth as a black body, we should have a temperature of around 5.3 degrees Celsius. Now you know this. If you're on the moon and you were to look back at the Earth, we can see it. So we know the Earth is not a black body. We know that it's reflecting a lot of that light, about 30% of it. And so if we were to take into account that reflection of light, then the Earth should be around negative 18 degrees Celsius. And this would be awful. All the water on the planet would be frozen. There's no way that life is going to be able to exist. And so what else do we have to add to this model? We have to add an atmosphere and the greenhouse effect. And what that does is it keeps heat close to the Earth. And so we should, and we do, have a temperature of around 14 degrees Celsius. And so that difference is just accounted for using the greenhouse effect. And so we really need the greenhouse effect. Where does it get its name? It comes from the greenhouse. And so how does a greenhouse work? Well, visible light is going to be coming through the glass itself. And so it's going to be reflected back, and it just goes right out of the greenhouse. You can look in a greenhouse and you can see things inside it, so you know the light is being reflected. Now let's look at light that is then converted into infrared radiation or heat. What happens to that? Well, when it hits the glass, some of it is going to be lost as heat to the environment, but some of it is refracted or bent back into the greenhouse. And that gets bounced around, we lose some of it, and so that heat is going to stay inside the greenhouse effect. Now, if we can limit convection or the movement of the air, then we can keep all that heat inside a greenhouse. It works a little bit different in our atmosphere. And so how does our atmosphere keep heat close to it? Well, let's look at what the atmosphere is made up of. It's mostly nitrogen, like 78% of it. We've got about 21% oxygen. We've got around 1% argon. And then there's this really tiny little black band right here, and that's going to represent everything else. Now, water can vary, and so we could have up to 4% of the atmosphere dealing with water, but we still have this really faint line here that you can't even see. And so what's inside there? Well, a lot of the greenhouse gases are inside there. And so what does that list contain? It contains water vapor, but it also contains carbon dioxide, methane, nitrous oxide, ozone, which is actually really important, and then chlorofluorocarbons. And a lot of those are produced by humans. And these are all greenhouse gases. And so how do they hold heat in? Well, I'm going to use a simulation to show you this. This is a PHET simulation. And so I'll put a link in the video description down below. I would encourage you to go there and check it out. But let's take a look at that. First thing you should look at is how visible photons and infrared photons interact with the gases that we're going to find in the atmosphere. And so in this simulation, we've got methane, we've got carbon dioxide, water vapor, nitrogen, and oxygen. So let me throw all of those into just a fake atmosphere. On the left side, we've got an emitter that is going to give off either visible radiation, light we'll call that, or infrared radiation. And so what do you think is going to happen when we hit these all with light? Assume that molecules can't move around. Well, if you watch this as the light moves through it, nothing happens. In other words, it's not affecting those molecules at all. Okay, so what happens if we turn off light and then we turn on infrared light? So this is going to be infrared photons. You should make predictions about what you think is going to happen. So let's turn this on now. So you can see that some of that heat is being bent and refracted, and it's actually coming back from where it was. Can you see a pattern of what molecules are vibrating? So let's see, I see methane is definitely vibrating right here. What else do we see? So there's another methane. I see carbon dioxide, so a carbon dioxide right here is moving. And what's the other big one that's moving? That would be water. So the water's vibrating and re-emitting that heat. If you look at things like nitrogen gas or oxygen gas, they're unaffected by heat. And so what does that tell us? Well, if our atmosphere was just made up of nitrogen and oxygen, light would come in, heat would go out, and we would have a really cold temperature on our planet. So we need these greenhouse gases. Let's take a look at how that affects our atmosphere at the level of the atmosphere itself. And so what I've done is turn back the clock a little bit. So we're in the last ice age. This shows our greenhouse gas compositions. Now this is thousands of years ago, and so you might think, like, who was keeping track of greenhouse gases at that point? Well, nobody. If we look at ice cores, what you'll see is there are layers in the ice cores where we had summer, winter, summer, winter, summer, winter, and so you can count back and figure out how long ago it was. And then little bubbles of the atmosphere are trapped in the ice. So we can take out a section, we can add it to a mass spectrometer, and we can figure out what's the composition. So we can see how much carbon dioxide, methane, or dinitrogen oxide, these are all greenhouse gases. Water, actually, we don't know because, the ice is water. But we can figure out what the composition was back then. And so what did it look like back then? We had a lot more ice for sure. And so watch what happens as a visible photon hits the ice. It just bounces right back again. And so as visible photons hit the ice, it's reflected back into space, so we're not getting that heat energy. If you look at photons then that are hitting the soil, they're being converted into infrared photons. And so we think of that as heat. And so as they move up, they're doing this kind of crazy dance. Some of them get refracted, some of them get bent back towards the atmosphere, and some eventually move off into heat. But since we have a low level of these greenhouse gases, we're not holding much of them to the planet. And so this area, we would have a temperature of around 34 degrees Fahrenheit. Let's move forward a little bit. So take a look at these greenhouse gas compositions. I'm going to move forward to 1750. And so what do we see then? Higher amounts of greenhouse gases. So these were actually recorded by people. So we have higher amounts. So what do we see now is an increase in temperature. What's causing that? We're holding more of that heat close to the planet. What happened when we got rid of all that ice, more of that light, instead of being bent back into space, it's actually being absorbed as heat. It's normal to see changes in the greenhouse gases, but let's look as we move forward from 1750 until today. And so especially look at these numbers right down here as we move forward. So we see huge increases in those greenhouse gases. Again, if we go from carbon dioxide, it was 280. I just checked today, it's well over 390, I think 397. We're pushing 400 parts per million. We're seeing huge increases in the other greenhouse gases, if you look at methane, for example. And so what's happening with that is we're seeing increase in the greenhouse effect. And a lot of this is caused by greenhouse gases that we're putting into the atmosphere. And so the industrialization has really increased amount of those greenhouse gases. And what we start to get is a greenhouse that kind of builds on itself. Let me talk about two ways that occurs. So for example, if we go back to the Ice Age, what happens as we start to melt the ice on our planet? Well, as we melt the ice on our planet, then there's more light being absorbed by the planet, and so it's going to increase that heat. Another thing that happens up in the north, that as we heat the permafrost, it releases a lot of methane. What happens with that? Well, it heats the earth more, so it releases more methane. Or you could think of the oceans, what's happening as we heat it up, then more water vapor moves into the atmosphere, which causes the earth get warmer, and so that's going to heat up the ocean even more. And so that's the greenhouse effect. Again, we need it. But man-made greenhouse effect is really causing global climate change that we're going to have to deal with over our lives. And I hope that was helpful.
Okay. So hopefully that was helpful. But you can see, I mean, we're definitely in a situation now where, and a lot of times I get into discussion with students and I say, hey, what do you think? If you could go back in time, you know, Doc and Marty and Back to the Future, you had your DeLorean and you went back in history and you wanted to find where do you think we went wrong and when did our situation change when it comes to these greenhouse gases, methane, carbon dioxide, when do you think that happened? And most times students know exactly when it happened, and that was the Industrial Revolution. You go back to the late 1800s, you know, 1860s, 1870s. That's when things really started to turn the corner. You know, the Industrial Revolution was, you could look at it both ways. It was a good thing, right? It got us into manufacturing and things like that, but it's coming at a cost, I think, an environmental cost. And I think that's where there's a delicate balance now in our society today is, yeah, we love technology and we love cell phones and satellite television and all the technology we have, Apple Watches, etc. But that's now, the earth is unfortunately paying a price for that production, that manufacturing, and we have to now change the way we produce things, or this is going to become the norm. It is unfortunately the norm now. It's becoming more the norm. This is a picture from June of 2019, so not that long ago. This is in Greenland, which is supposed to be a major ice sheet. And you can see these sled dogs. You know, they're not going through ice. They're going through melted water. Or melted ice and through water, unfortunately. And this is what you're seeing. And in fact, I believe statistics, and if you look at the data, the North Pole and Greenland and places like that are seeing the largest temperature increase of any part of the Earth. Not that we're not staying frozen either, but as far as increase in temperature percentage, the highest percentage of temperature increases over the last, I would say, decade, maybe 2 decades, it has been places like this, like Greenland, like the North Pole, northern Alaska, places like that, which are starting to see more and more of this and less ice. sadly. So that's something that we definitely have to keep pushing toward, changing the way we manufacture things, changing the way we drive our cars, right? Cars have to, get away from the dependence on oil and gasoline. The way we heat our homes, the way we produce our electric, all of that is causing great effects on our climate, and we have to start to really act. The talking has got to end, and the action has to really get going, and at a faster pace, or Earth is going to continue, unfortunately, to suffer in the near future. And we're seeing it now. It's not something you can say, well, Mr. Rocco, it's not going to happen for another 20, 30 years. No, it's happening now. We definitely see it. You're living through it. And so if we want a better future for our future generations, we really have to act now and start changing changing our ways, I guess. This is where your greenhouse gases, or what the breakdown of greenhouse gases. So 64% of your greenhouse gas is CO2. 17% is methane. Now this data is old. This is, old in relation. It's 2014. So you're talking going back now 7 years ago, but the numbers would be pretty similar. So still a lot CO2, a lot is methane. Your CFCs, your chlorofluorocarbons. Nitrous oxide. Nitrous oxide is a laughing gas. I don't know if I've gone to the dentist. I remember when I had my wisdom teeth taken out, and they gave me laughing gas. So that's a greenhouse gas, nitrous oxide. And then you have a very small fraction of what are called fluorinated gases. These are man-made gases. Unfortunately, it says here they stay in the atmosphere for centuries. It's not a gas that just dissipates right away. I mean, centuries and centuries, those fluorinated gases will kind of get stuck up there in the atmosphere. This is your source of your greenhouse gas. So again, this is going back to 2014 now, so not the most up-to-date data, but still probably similar today, even in the year 2021. Electricity, again, 30% of our greenhouse gases is still coming from electric production. 26% of greenhouse gases is your cars, your buses, your trucks. 21% is industry, manufacturing. 9% is agriculture. And 12% is, again, heating your house and producing that kind of stuff. So we need to definitely fix these numbers. Again, electric. You are starting to see more clean electric. Windmills are popping up. Wind farms are popping up more often. Hydroelectric power, I'm starting to see more of that coming out too, where they just use water, spin a turbine, which produces electric. But I just don't think, in my opinion, it's happening fast enough. I think we really got to push this stuff quicker, faster, really get our climate in check. Cars, definitely. We shouldn't be using gasoline to run our cars anymore. We should be using some, whether it's solar or some other, electric cars. A Tesla, but produce the electric clean. So electric cars can be fine. But just we have to produce our electric in a clean fashion. And then it's a win-win. You're running an electric car with zero emissions, and you're producing your electric in a clean fashion. That would be a win. I guess the problem, I think, with electric cars, unfortunately, right now is just how far you can go. I mean, I don't know off the top of my head. Maybe some of you know better than I do. I mean, electric cars can only go so many miles on a charge before you have to stop and charge them. They're getting better. We just still have a ways to go before you'll be able to take a trip from, let's say, Rhinebeck to Florida and not have to keep stopping over and over and over and over again to keep charging your car. But as those batteries get more powerful and can go further, and I think that's happening, and you're seeing that slowly, then it's just a matter of producing that electric in a clean fashion, and then it's a win for everybody. These are just showing you your greenhouse gases from 1990 to 2010. This is in millions of metric tons of CO2. Millions of metric tons of CO2 equivalent, I should say. So you've got, you can see the trend is up, right? 1990, you can see how many metric tons of CO2, methane, nitrous oxide fluorinated gases. And you can see that number definitely, especially if you just take the CO2 levels, as you can see slowly from 1990 to 2010 how they've increased. And this is not even including from now 2010 to 2020, where the trend is again still going, unfortunately, in this direction. Again, these are your greenhouse gases. You should know them. They will ask you from time to time on a Regents question, might say, just list 2 or 3 greenhouse gases. So you've got your CO2, your carbon dioxide, clouds. Again, remember we talked about in a previous video, clouds do trap heat. That's one of their purposes. Besides blocking out sunlight, their other purpose was to keep a blanket on, right? Just like you use a blanket at night. So they are there to trap heat. So that's technically a greenhouse gas. Methane and nitrous oxide. The guy also talked about in the video, he talked about CFCs, which chlorofluorocarbons, that would also be a greenhouse gas. Ozone to a certain extent, because ozone traps the ultraviolet, which then gets turned into heat. So ozone is also technically a greenhouse gas. So you've got CO2, clouds, methane, nitrous oxide. And again, I would add the CFCs down here, and I would also add ozone. These are all greenhouse gases. The Regents will ask sometimes for, 2 or 3. So you should be familiar with these gases. This is a direct relationship. So you've got a red line and a blue line here on this graph. The red line is showing you temperature. The blue graph is showing you CO2. And this is going back hundreds of thousands of years ago. And you can see definitely a pattern here. When one goes up, so does the other. So as CO2 levels increase, this is going back 300,000 years ago, so did temperature, right? It's greenhouse gas, going to trap more heat. As CO2 levels dropped, so did temperatures. 200,000 years ago, CO2 levels went up, so did temperature. And you see that same pattern. As temperature, CO2 levels increased, so did temperature. This is showing you up to 2007. So again, this is a little bit outdated, but you can see the trend here. And that's what the gentleman was talking about in the video there. He goes by what are called ppms. ppm stands for parts per million. So they look at how many molecules of CO2 compared to how many molecules of nitrogen and oxygen. And you don't want this number in this range. In fact, it's probably a lot higher than this now. But this was back in 2007. We were pushing 400 parts per million of CO2. I would, if I had to speculate right now and I'm looking at the data, it's probably still there. It's probably closer to 500 parts per million. Which is pretty scary. So when you're getting to that 400, 500 parts per million range of CO2, you can only imagine where temperatures are going, right? Temperatures will follow with the parts per million of CO2, right? So it's a direct relationship. As one goes up, so does the other. This is going to show you fossil fuel burning, and this is from the 1700s, mid-1700s, like he had showed in that simulation, up to 2012. And again, if you look at CO2 or fossil fuel burning and the CO2 emissions, you can see 1750, 1800, nothing. You got to 1850, just started to turn the corner. And once you got past 1850, here's your Industrial Revolution, right about in this section, that's when we started to really get into the CO2 production and burning fossil fuels, right, manufacturing during the Industrial Revolution. And look what's happened to that CO2 level, how it's skyrocketed as we've gone now to 2012, which is, let's say, right here. And unfortunately, the question mark is, where will this peak? Where are we going to reach the peak? Where are we going to hit the top of the mountain? No one knows, right? Hopefully, as countries slow down on the CO2 production, right, this graph will start to hopefully turn the corner and go back this way again. So we can only hope, but that's going to take time. That's going to take time. This also shows CO2 emissions. This is more recent, 2015. As far as countries, which countries are the worst? And I put that in the other video when I showed you those aerosols, and it showed the different colors and going through a time lapse of the year. But you can see China is 28% is CO2 emissions from China. We're still up there, 15%. Not as bad as China, but we're still producing quite a bit. India, which has a lot of manufacturing, at 6%, Russia at 5%. So these are some of the worst polluters. The rest of the world right here is make up 21%, and then all of these are separate. Countries that are 1, 2, 3, 4%. Japan, Germany, Canada's only at 2%. Mexico 1%, United Kingdom 1%, Australia. A lot of these are 1%, Italy, France. But definitely China and the United States right there alone, make up a pretty good chunk of this pie graph, unfortunately. What can you do? So a lot of things you can do in your house, even just turning off a light. You leave a room, just flip the switch off, put things on timers. Upstate New York might be hard to go without a car, but if you live, like I do in the village, you take a walk, ride a bike, carpooling, thinking about using solar. I know I've had a discussion with a lot of you. You have solar panels. That's excellent. That's how you produce your electric. Geothermal, where you're using geothermal to heat and air condition your house. That's also a big thing. Insulating, just making sure your house is well insulated. That actually saves on your energy costs, but it helps with the environment, believe it or not. LED bulbs. I wouldn't even go with these fluorescent anymore. I would stick with the LEDs, right? They're the best. They use pennies of electric. They don't waste a lot of energy, produce a nice bright light. Unplugging your phone, after it's charged. I think and I'm not an expert on cell phones, but I believe the best way to use your phone is to really use the battery almost down to when it's almost empty. Don't let it get to the point where it's empty, obviously, and then you need it in an emergency, but let it get down to 10% and then plug it in, charge it. Once it's at 100%, unplug it instead of leaving it on the charger. Programmable thermostats are great. Something like a Nest, or even just a programmable thermostat in general. If everybody leaves the house in the morning to go to work and school, have that thermostat automatically drop at a certain temperature and come down during the day. Why heat your house when no one's around? And then let's say half hour or so before the first person's going to come home in the afternoon, have the heat turn back on again to heat your house. Save your energy costs. Nighttime. I know I have my thermostat will do that. It'll drop. It's best to sleep at night in a cooler situation. You don't want to have too hot at night and you're sweating. So it's better to have your house cool down at night. So at around 10 o'clock, my thermostat will drop automatically, come down, and keeps the house cooler, and it's better for sleeping, and it saves energy costs. All right, and the last thing I'm going to touch on, this is called insulation temperature lag. The word lag means to kind of fall behind. Usually you hear the word lag, you talk about jet lag. Let's say you flew from New York to California, or the other way. California, you have relatives in LA, and they flew to New York. Well, when they fly across the country, they're changing time zones rapidly, right? A few hours on an airplane, but all of a sudden now the time change, right? And it takes your body a little bit of time to get used to that time change. Some of you maybe have traveled to Europe, right? When you get off the plane in Europe, all of a sudden you're feeling kind of tired, kind of sluggish. The time change has kind of messed up your body. So you have what they call jet lag, right? The jet was ahead of your body, and your body kind of lags behind now. And so the same kind of idea happens with the sun and temperature. And basically what happens is, because we have an atmosphere, and this goes back to in the other video I was talking about oven. I said, think of the earth like preheating an oven. The temperature is always going to be a little bit behind the sun. And so it says the hottest time of the day occurs a few hours after noontime. So yeah, solar noon is when the sun is at its most intense, around 12 o'clock. But we don't reach our peak temperature until a couple hours later, 1, 2, 3 o'clock in the afternoon. And that's this lag. So the sun is always going to be a little bit ahead of our temperature. We're going to reach our peak sun at noon, but we're not going to reach our peak temperature until 2 or 3 hours later. That happens on a daily basis. It also happens on a seasonal basis. The hottest time of the year is about 6 weeks after the summer solstice. So yes, we reach our longest day on June 21. That's our longest day of the year. But we don't reach our peak temperatures until late July or even early August. A lot of times you might have heard August is known as the dog days of summer. What do they mean by that? It's hot. I think of a dog panting, needing water, right? Got his tongue out. That's the dog days of summer, but that doesn't come until late July or August. So there's always going to be a little bit of a lag, and that goes back to this whole thing we talked about when it comes to preheating the oven. The sunlight has to go into the ground, and the ground has to then turn that energy into infrared, into heat. And then those heat waves have to come out of the ground. Well, that takes time. And that's that atmosphere that causes that. And so because Earth has an atmosphere, there is going to be this lag of temperature behind the sun. Sun reaches its peak at noon, but the peak temp is a couple hours later. We reach our peak sun on June 21, but we don't reach our hottest temperatures till late July or August. So there's always going to be a little bit of a lag in our temperature behind the sun. It's a couple of hours every day, and it's 6 weeks when it comes to seasons. Okay, so strongest sun at noon, hottest temperature 2-3 hours later. Strongest sun June 21, summer solstice, hottest temperature late July, August, early August. And I think that is it. This just talks about the same thing again, so I'm going to skip through all that. Yes, that would be it. All right, so I will post this video again on my YouTube channel. Please make sure you watch all 3 videos carefully. Rewind things that don't make any sense. You always have office hours on Wednesdays from 9 to 11. You can pop on to ask me any questions if any of this stuff in the videos this week didn't make any sense. And I will talk to you soon. I hope you're all safe and all doing well. And I'll talk to you soon. Bye.